So this is the second video for Chapter 9, AP Physics, Paul A. Tipler Physics book, 4th edition. I'm going to talk about applications of Newton's second law and remind you that the Newton's second law in linear land is F equal ma, and when we talk about rotational land, it's tau equal I alpha. I'll remind you about I is the moment of inertia, and depending on the shape, there's a different formula to calculate I. There'll be a chart that has those shapes and formulas on your test. Don't believe there's one on the AP test, so you're going to have to find some similarities in them so you can, because there's like 10 or 12. You'll need to see what's common in most of them and try to figure out one or two things to memorize. So when a round or spherical object rolls without slipping, the track it makes is similar to a tangent. So think about a circle, any kind of circle, and a tangent would be that line that touches one point on the outside and is perpendicular to a radius. As something rolls, the track it leaves behind resembles that tangent. Also, if you have a pulley that has a belt around it, or a pulley that has a chain around, like on a bicycle chain, any type of straight path or belt or pulley driven chain is going to be just like a tangent. Think of all of those as being tangent to this circle. And all the problems like that, including one of these rolling down a hill, those would always be figured as the velocity moving forward is the same as the tangent velocity it leaves behind. So that's the way to think about that. And the formula for velocity tangent v sub t is big R times omega. R is the radius and omega is the rotational velocity. Of course, tangential acceleration, if you're required to solve for that. Again, it's the radius times the circular acceleration, rotational acceleration. So those are the types of applications that you would look for in these problems, and they're pretty common on the AP test. So if they were going to give you a problem from this chapter, I'm thinking it's probably going to be that type of problem. The other type of problem would be the object rolling down the hill to calculate what speed or acceleration it's going to have at the bottom of a hill. All right, so we'll move forward on that. Rotational kinetic energy. So I've got a problem that's a really good problem that's solved step by step by step. It would be a good idea for you to get that and look through it. Ran some copies of it, and I'm going to go over that pretty much step by step. So what will be involved will be a wheel or a sphere or a ball rolling down a hill, and they will ask you a number of possible questions, one of them being what would be the velocity of the wheel, the linear velocity of the wheel when you get to the bottom of the hill. Possibly what would be the acceleration when you get down to the bottom of the hill, linear acceleration. And this is practice problem 8E, and it actually comes from a different physics book. So it says a solid ball with a mass of 4.10 kilograms, so that's your mass, radius of 0.050 meters, starts from rest at the top of a height of 2 meters and rolls down a 30-degree slope as shown in figure 8.15. What's the translational speed of the ball when it leaves the incline? So when it gets down to the bottom. So you know that it's 2 meters high. So h is 2.0 meters. The angular displacement is 30 degrees. Mass is 4.10 kilograms. Radius is 0.050 meters, and the velocity initial is 0.0, and they're asking what's the velocity final. So we're going to use the conservation of mechanical energy in order to solve that. So if you look at the problem, you'll see that we're starting out with mechanical energy initial equals mechanical energy final. So we know that mechanical energy is conserved. And mechanical energy initial can be kinetic plus potential plus spring energy or any of those, but really it's not all of those, it's only one of them. It is the potential energy gravitational, MGH, because it's at rest at the top of the hill. So we start out with everything in MGH. You know the mass, you know G is 9.81 meters per second squared, and you know H is the height of 2 meters. On the other side, we have several things going. We've got the wheel moving in a linear movement, kinetic energy equals KE equals 1/2 mv squared, and we also have rotational kinetic energy, which is 1/2 I omega final squared. So we know that omega final equals velocity final over r, so we can make that substitution for omega. So instead of 1/2 I omega squared, it's going to be 1/2 I velocity final over r. And we also can solve for I for this sphere, and we look at the chart and we find out that the value or the formula for moment of inertia is 2/5 mr squared. So we substitute that in for I. Now we have 1/2 times 2/5 mr squared times v final over r squared, and when you multiply all that out, you end up with your kinetic energy translational, which is 1/2 mv squared plus 1/5 mv squared, which equals 7/10 mv final squared. So the v final is what we're solving for. When we do the algebra on that, you see that v final squared is equal to 10/7 g times h. And because the masses all cancel, mass is the same on left and the right, so they all cancel. And then we figure that v final squared is 10/7 times 9.81 meters per second squared times the h, which is 2 meters. And you see that velocity final is 5.29 meters per second. All shapes can be solved the same way. They're going to have a little bit different I, so you have to look at the chart and substitute in the I value. But look through the solution for that, because you're going to have a problem like that on the test. You're more than likely, if they have one from this chapter, it's going to be a problem like that that you see on the AP test also. So I'd like for you to look through that, and then on the other side, you'll see there's a conservation of energy practice 8E problem number 1, and it says repeat sample problem 8E using a solid cylinder of the same mass and radius as the ball, releasing it from the same height, and you're going to try to see the race and try to show your work and see which one would win. So try that and make sure that you can work that type of problem. Rolling with slipping. So this was a problem rolling without slipping, and obviously if you're on a slippery surface that has a low coefficient of friction, the chances are it might just slide down. Well, when it starts sliding down, there's a point in time where we'll meet a requirement, which is the velocity of the center of mass is equal to r omega. Once we get to that point, then it will start rolling again. So, you know, there's some problems that may involve a lower coefficient of friction where there will be slipping instead of rolling without slipping. So you need to make sure that you check the problem and see if it says with or without slipping, because that'll make a difference on how you solve it. So the final section talks about power, and of course power is the change in work per time, and if we adapt that to our radial system, then torque times the change in angle, which is our distance. Remember, work is force times distance. Tau times the angle divided by the time, which equals torque times omega, which is angular velocity. So that gives you some different options for how to solve for power. And remember, power is in watts, be the SI unit. So that finishes it up. Fairly short chapter. Not an easy chapter, but a short one. And go through and work as many of the sample problems as you can. And run through it. If you need to see something else, look through the practice problems, especially that one from the other book. Make sure you work through that step by step, because you're going to see one like that on the test. Quite well could see one like that on the AP test. All right, work hard. We'll see you on the next video.